Okay, this is section 13.2, line integrals, and hopefully you've watched the first two short videos on just the overview and the visual of a line integral. If not, go ahead and take a look at those or maybe revert back to those at some point just to get a sense of what we're trying to accomplish by calculating these line integrals. You'll see that, as we do this, a line integral is kind of maybe a poor term. It's maybe better called a curve integral, just because we're looking at, in space. If we look at our diagram here, we're looking at this curve in space, and the area between that curve, if we were to sort of drop a sheet or a curtain down from it down to the XY plane. And what you will see in a lot of these diagrams, or in this one in particular, is that there is a sort of a projection of that curve on the XY plane. And so we're just trying to find the space in between that. And if that space dips below the XY plane, then it would be a negative contribution to the overall area. And if it's above, then it's a positive contribution. I'm going to try to kind of explain where the formula comes from. Now you have your two definitions here. These are from our textbook, and we're going to obviously rely primarily not on the Riemann sum definition per se, but just this second one right here. That's going to be one of our main formulas. But let me try to explain where it comes from. So if we think about a Riemann sum as we do with definite integrals, we have a height associated with our space curve, which is going to be here labeled as f of xy. We're going to do write the equation of the space curve in terms of the parameter t. So when we look at the particular space curve, we're going to write it as a function x of t and a function y of t. And so this is going to essentially be a calculation of the height of any particular, rectangle that we would form. And you can see over in this diagram, there are a lot of these little rectangles that are forming. And so the height of the rectangle is the function value. But again, the function we're gonna write is gonna be in terms of a parameter t. So in other words, we're gonna set up for our space curve a function r of t, or a vector, excuse me, r of t, which will be two components, x of t, and then it will be y of t. Okay, so then when we look at the base of the rectangle, so let's just take, for instance, this little section right here. That base of the rectangle would be a specific arc length. And so that particular arc length we're going to call S. And if we think back all the way to chapter 10, this was in section, I think it was 10.3, we talked about finding arc length and the formula for it, which is listed here in our notes as L. You can call it S or whatever you'd like to call it. But when we talked about it in 10.3, we called it S, and we calculated ds, which is the differential for arc length. And that differential would represent a small change in the arc length. So if we're setting up these rectangles for our Riemann sum, which then converts to our definite integral, if we're looking at the base of a rectangle here, or in other words, a little change in that arc length, ds that we developed in section 10.3 was the square root of dx dt squared plus dy dt squared. And if you look over at our, and then times dt. So this differential, if you notice, is the exact value of the differential in our formula for, in this case, our line integral. Okay, so what we're doing with our formula then is that we're taking our height, which is f of xy, we are converting it into parametric form. So we're going to convert it into x of t, y of t. And then ds is the differential. So we are going to integrate not with respect to x or with respect to y yet, but we're going to integrate with respect to arc length. And that differential ds, we're going to need to convert to be in terms of t. And the reason we need to do that is because our entire integrand will be in terms of t, so we need a dt there. And so when we convert ds, the differential arc length, we're going to convert it into the differential dt, but we need to multiply by the square root of all of this because the differential ds is equal to all of that. Now, how does this connect specifically to, in this case, if we have r of t, an equation of r of t? Well, basically, and I'd say this is an easier way to understand this, is that what we're really calculating here is the integral from, let's say, a to b of f of r, the vector r of t. So we're going to plug in x of t and y of t, and then we're going to multiply by the square root of all of that, which is really just the magnitude of r prime dt. So this, again, is just another way to represent this particular formula, but it might be a little bit easier to remember, and it's a little bit smaller. So let's try example 1. Let's see if we can make sense of any of this stuff. So example 1 says we're going to evaluate this particular line integral, and c, so the path that we're taking, is the upper half of the circle x squared plus y squared equal to 1. So let's go ahead and draw out our path. Our path is just the upper half of this circle with radius 1. So we're going to go from -1 to 1, and we need to write a parametric equation for this circle, and we've done this a bunch of times. The one that we've used most commonly is x equal to cosine of t, and then y equal to sine of t. So we're going to represent our vector r as cosine t, sine t, and we're going to need r prime. So let's let me write this as r of t. Okay, so then we need r prime, which is negative sine of t and cosine t. And then we also need the magnitude of r prime. And we've done that a bunch of times. That's just 1. That's going to be the square root of sine squared plus cosine squared equal to 1. So a pretty easy transformation here. So what we're going to take is our line integral, which is 2 plus x squared times y ds. And we're going to convert that into the line integral of, I'm just going to write it as f of the vector r of t for right now, times 1, which comes from that, okay, and then times dt. Okay, so let's do our full transformation of variables here. So we have the integral. Now we're going to go from a to b, and in this case, if we're just doing the top half of this circle, we're going to go from 0 radians to pi, and then we have 2 plus, instead of x squared, we're going to have cosine squared t, and then instead of y, we're going to have sine of t, and then we're going to multiply by 1, and then by dt. So that's our line integral. So that's our setup. At this point, now we're just doing all the stuff that we've done for quite a while now. We're just going to calculate this particular single integral. So to do this, we're going to need a u substitution specifically for this part. So we'll just do this sort of off to the side. And we've done ones like this before, so this one might be one that you have memorized. So this integral will be negative u squared du, which is negative 1/3 u cubed, which converts back to negative 1/3 cosine cubed t. Okay, so that's our u substitution, and so let's do the full integral. So we have the antiderivative of 2, which is 2t, minus 1/3 cosine cubed t, and we'll evaluate from 0 to pi. So we get 2 pi minus 1/3 cosine of pi. Cosine of pi is negative 1, so we have plus 1/3. And then minus 0, and then minus 1/3. So we get for an answer 2 plus 2/3. So that's the area underneath this particular curve on that particular surface.